everybody, welcome back to the podcast Everyday Metallurgy. We are in the middle of an episode on battery materials with Sven Fleischmann. We have talked about some of the material that goes into it, especially focus on lithium, but we'll continue today looking into some of the metal oxides, especially cobalt, and take a deeper dive into that. So enjoy the show with Sven.
Depleted, and in fact the next generation could be this all solid state battery, and then it's going to be a metallic lithium anode, and then any type of cathode material that gives a good energy density, and then I would say we are back with metallurgy.
Yeah. I hear a lot of talk about other materials that you have not mentioned, cobalt especially, because cobalt is a problem. It's they call it a conflict material. It's only mined few places, and we lack it. There's nickel, there's manganese. Where do we find these metals in a battery?
Yes, so it's at the cathode. So we are moving away from the sulfur topic and we go back to the classical lithium ion battery. So we have talked about the anode, it's the graphite lithium anode, the separator, the electrolyte, the components in the electrolyte. Let's focus on the cathode.
Yeah.
Cathode materials, they need one characteristics, and this is their ability to accommodate, to store lithium ions, of course. So, and what was found very efficient to do the job is certain type of oxide materials. So, and in lithium ion batteries, some sort of benchmark for many, many years was the cobalt oxide, lithium cobalt oxide. Yeah. So you had lithium, you had cobalt in this oxidized form, and this was really something like the standard generation and still used today of lithium ion batteries.
So pure cobalt oxide?
Pure cobalt oxide. So when Tesla introduced their first models, and I think well into their models, 10 years ago, their standard material was lithium cobalt oxides. So, and the lithium cobalt oxide has had one charming experience. It has a very good cyclability. So you can really cycle it forth and back a lot. So it's very stable. There is no degradation over time. It's also safe. There is a good track record because these cathode materials in lithium ion batteries, they have been around for decades, I would like to say, because this is the materials we solely started off, and this is our daily life experience when you had this Walkman, or still you have these cells, a AAA battery, AA battery or so. So this is lithium cobalt oxide. Very safe material, and Elon Musk decided, I don't want to go for the fancy stuff. I need to develop an electric vehicle that needs to drive, that must be safe. And he has chosen, or the team has chosen, lithium cobalt oxide, obviously, and it did the job. So it was a little bit of a shock for developers at that time that Tesla was referring to such an old type of cathode material, but simply it was around and it had a good track record. Now things are changing. I mean, now these materials are not sufficient anymore, I would say, for a variety of reasons. So one reason is their energy density is not the highest. So you can improve the energy density by referring over to other types of oxide materials. Yeah. And of course, cobalt is very expensive. When you look at the London exchange pricing, it's fluctuating quite a lot. Prices can be extremely high. Yeah. And this is, of course, something that is not facilitating this growth in electromobility. So you would like to have something more constant. Yeah.
Yeah.
And so there is then the quest to find alternative materials. There is lithium iron phosphate. That is also a good solution. They are also very stable, very reliable battery materials, but their energy density is still a little bit lower than the lithium cobalt oxides.
Okay.
And so then what people are doing, they mix. So what you do, there is one component that is good, is really good, but it has certain disadvantages. Well, you try to formulate out. Yeah, you try to reduce the amount and put in, let's say, some dump material. Let's put it that way.
Yeah. So
And there is
dilute the cobalt.
dilute the cobalt exactly
Yeah.
in this oxide material. And there is this, you can call it the magic triangle of the composition. So you have cobalt, you have manganese, and you have nickel. So these are the three essential metals for these oxide formations in batteries. So cobalt, for its good capabilities. Nickel has also good capabilities that it's stabilizing the battery even more. And manganese is still electrochemical active, but it's a cheap material. So, and you're trying to find simply a good compromise, and you can move around there with the chemistry. You can play around.
I'm just breaking in because cobalt, I think we need to take a deeper dive into that, because we call cobalt a conflict material. And what does that really mean? It means that cobalt comes out of Congo, and in Congo there's a big conflict going on. So the raw material you dig in that area, they are financing civil war. On the list you also find gold, you find tantalum, you find tin, and you find tungsten. So all these materials can be conflict material, but you can also get conflict-free material that are mined in non-conflict zones. So it's not all that is conflict, but as 50% or more of the cobalt that is mined in the world today comes out of Congo, there's a pretty big risk that you have conflict material in the battery in your car or in your cell phone. So back to Sven and the batteries.
Then if we look into the battery and how it works, a lithium ion gives away one electron. And that gives a voltage drop. How much do you get per, is it called per cell?
Yeah, so lithium in lithium ion batteries, lithium is always in the oxidized state. So lithium will never accommodate an electron and give it back. So it will share the electron with the graphite, but it's never really reduced to metallic lithium again. And it's also not giving this electron away. It's a different mechanism. So the voltage of the cell is relatively low. So that's maybe also an interesting thing. I mean, what determines the power of a unit cell? It's basically a product of the capacity, so the storage capacity in milliamperes per kilogram or so, and the voltage. So you have to multiply the voltage times the capacity. So if you increase the capacity or the voltage, you get higher power density. Usually with the voltage, you are fixed with the system that you're choosing. It's determined by the cell component. So the anode component and the cathode component, and there is the resulting voltage. Period. There you cannot move around. So the only measure you have then is increase the capacity, and there you can fine tune the materials as we have described, and then really go for the maximum.
And what is a typical voltage drop in a unit cell for a lithium-ion battery?
This can be severe. I mean, really going depending on the system again. In a good functional cell, I mean, it's in a low percentage range. Yeah, for materials when we have these side reactions, it's severe. I mean, even after very short cycles, 10 cycles, 20 cycles, and so on and so forth, you have severe voltage drops, could be 20% or so. In lithium-ion batteries, I mean, you really have this only after many cycle times. I mean, thousands or so, where you have significant voltage drops.
Yeah.
There is one trick that so when you are an engineer or a chemist, a researcher, a scientist, and you are really focusing on the materials development, you do your job, you know, you fine tune everything. But what's then done in a car with the engineers is, you know, they also add different components. They add safety features, for instance. They add, let's say, intelligence. I mean, a car, an electric car with their batteries, does not just come with batteries, but it has a very elaborated management system for the battery. So it needs heating, cooling, and so on and so forth. Everything needs to be managed and electronically, and so on and so forth. So usually, when you buy an electric vehicle, you only start working with, let's say, 80% of the cells that are ready. And when these cells are kind of depleting, when first cells may even drop out entirely, others are degrading, a program basically then enables to access other cells that are virgin, that were not used before. So you can maintain the experience for the driver of a very high lifetime, although you start deplete and work down your single cells the very first moment, of course. But so that is how companies are doing that, and this can be done, you know, by simply a trick in the battery management program. There was some incident, when this became very apparent to me. Some years back, there was a fire in California. And, you know, California in the United States is one of the states that is promoting electric vehicles quite strongly.
Yeah.
And so people had to move out certain areas of California because there a forest was burning. Yeah, there were these devastating problems some time ago. And what Tesla did, kind of they operated, they sent a code, and the drivers could extend their driving range by many percentages for this time, just to flee, just to get out of this area, because it was on fire. It was a hot spot, and they needed to get out. And then for this incident, Tesla kind of for a day or two, they opened up their full capacity of the cars, of these batteries, and closed it again after some days. So we are moving. This concept of an electric vehicle is very different from a combustion engine. So things are controlled more from a central stage, especially with Tesla, I think. I don't know how the others are doing it. And so it's not what you fill in your tank, like the gasoline or so. It's more the management and, you know, the support that you get, like online, from your provider, how much energy I can really access from the battery. So that's a very different kind of concept. So that's different if you as a scientist, you know, fine tune everything, but then in reality, you know, there's so much more engineering on top, and the product looks very different from what you started with.
Maybe a stupid question, but is the weight of a battery the same when it's fully charged and when it's fully unloaded?
It's the same. Yeah. I would.
So you don't charge electrons on it?
No. I mean, it's a closed system. I mean, you take the energy of the electrons, but you don't take away mass or so. Yeah. I mean, if you have a malfunction, you know, it can be that the electrolyte is evaporating, but then that's a problem. Yeah. Then something is damaged. It's not good. But usually, you know, that is a zero mass balance.
I live in a cold spot on the earth, and in wintertime, when I bring my cell phone with me outside, when I go out, it could be almost fully charged, but after half an hour, it doesn't work because it's -5, -10 degrees C. Why is that happening?
Yeah, my explanation is that it's the electrolyte. So it's getting more viscous. So when you kind of in these cold winter times, for batteries, everything is about mobility. The ion need flow swiftly forth and back. And if this is prohibited by some external means because it's too cold, and cold means, molecular movement is reduced. So that is one aspect why this is happening. And if then you go into your office where it's cozy and warm, then your capacity even goes up again. So, and this is
It'll come
really
back.
a comeback. Yeah, that's the thing. Yeah, yeah.
Yeah.
On the way,
And
you also then use more energy because there's more work involved. I mean, when the battery even needs to function, think about a car. You drive outside at -10 degrees. Of course, over the time, the battery also involves some heat, and in fact, there is some heat management needed to remove the heat. But this will take some time until this effect comes into play. So if you drive short distances, the work for the battery to move your car will simply be higher because it needs to overcome this internal resistance, kind of, with the higher viscosity and the smaller movements. And so you feel that. So then your battery discharges really more rapidly. So that's a real effect that comes into place also.
I can see it I have an electrical car, and summertime I can go 450 kilometer on a charge, but in winter time it's often reduced with 100 kilometer.
Yeah. Yes. Yeah.
Mm.
And that's the effect. Yeah.
Yeah.
And this will stay fundamentally. So there's a way how this can be changed. This is an intrinsic problem of batteries. Yeah. So you will always have the effect. The question is, I mean, if this effect will be seen also dominating, let's say, with the future cell batteries. That's the question, and I cannot answer this. So when you have these all solid state batteries, so no
then should be
liquid
no problem.
electrolyte. Yeah, but then you have a problem of migration per se. So when you have ions need something, they need a medium to move from one to the other side, forth and back easily. So if the medium is rigid by itself, it's the problem. I mean, it's a tougher job. So what people are typically using, you need a kind of electrolyte. So without electrolyte, you cannot work. So the electrolyte is, of course, a salt, a lithium ion salt, special types of salt. So it's not lithium chloride or so, it's different types of salts. In a classical aspect, of course, the liquid, the solvent, and in these solid state batteries, it's usually a polymer. It's a polymer that has a high flexibility, has a very low glass transition point, but these still have a very low lithium ion conductivity. So usually these cells, they only operate at elevated temperature. Even if you have so I said that you can use polymers, but you also can do ceramics. Ceramics, I would say, depending on the type of ceramic, could be oxide, could be sulfides, could be glasses even. Yeah, so there are a lot of options, but even there you need elevated temperatures very often. So I'm talking about 60 C or so. I think this effect may even be more pronounced. So you need something to preheat even, perhaps. Yeah. So I don't know. I see that a challenge. Yeah.
So I have a few more questions left. Well, if you bring such a battery with you into space, very often out there it's pretty cold on the dark side, and very warm on the sunny side. So do they have special batteries for space exploration?
Oh, that's a good question. I would. The question is if I would resort to a lithium-ion battery. I probably don't think so. I mean, only for for small applications, of course. Yeah. I would say for vital applications, of course, you need duplicity and independent energy backups.
Yeah.
So probably even something like a fuel cell, which is also a type of battery, if you may think so.
Yeah.
But of course, also some kind of small reactor or so. I don't know how they charge the solar energy, with and then batteries must be the case. I mean, it's a good question. I never thought about this.
Yeah.
We have to look that up.
Yeah.
Yeah.
And then very often when you look at a battery, it's small single cells that are put together in series to, I guess, to bring up the voltage level. But
Yes.
why are they this small? How big can you make a battery? And is there a reason for not making it bigger than they are?
Yeah, I would say a small design has advantages. So first of all, think about production. I mean, I think if you have, let's say, a moderate size, also not tiny or not too big, it's different. So if you have, you can easily, take it out and remove it if there is a malfunction cell or so. Rather, if you have like a big chunk of single cell, may not be so convenient. So how are batteries again made? So it's a casting process. So you work with slurries. So that's more or less an automated system. It's, I would say, even continuous. So you have rolls of copper foil, of aluminum foil, which are the current collector for anode and cathode. You cast on top of that the anode and the cathode. You dry it and so on and so forth. So this is an endless production. Yeah, as long as the coil is, and then you have to refeed a new coil, and then you cut it into pieces. So what's typically done is these batteries are. Let me check if I have something. These batteries are rolled, and these are classic dimensions. Yeah, so
Exactly.
this is a classical battery, and
Yeah.
if I open that up, there would be probably, I don't know, maybe 2 meters of a foil, probably of 5 centimeter width or so.
Yeah. Yeah.
On one side, you have the anode, on the other side the cathode, and then it's rolled, a separator in between, and then you bring it in touch, and this is how you design a battery. So it's I think it's not a rocket science. It on the paper always things are a little bit easier, but it's, I would say, quite straightforward. And you can also make this very reliable. Yeah.
Yeah. A last question, Sven. Where will we be in the future? Will there be extremely new applications? Will we be able to use batteries like these for high power energy storage? We talk a lot about electrification and going wind turbines, solar panels. But can we use these batteries the day the sun is not shining and the wind is not blowing?
I mean, this is also connected to the costs. So when you think about mobility, I mean, the target application is for cars, for electric vehicles. I'm aware that also it's used in aviation. So there are types of not aeroplanes, but let's say drones around, that are equipped with some sort of metallic lithium batteries, for instance. That is the reality today. I personally would not see this with a passenger plane. It's, I would say, the imminent risk behind that, you know, um, maybe in a very far future, this could be the case. For storage batteries, like immobile applications, I would see we will see more of these applications. And there is one country that is very much advanced, and this is respect, and this is Japan. Japan has been a battery country for many decades, thanks to Sony, but they are working around with all types of batteries, and they have, real big batteries in place. That is another type of battery. It's named sodium sulfur battery. So this is a battery that is not especially lightweight, but for immobile applications, you don't need, you don't
if it's
have to
cheap.
be concerned if it's exactly, and that's the reason. So sodium is cheap, sulfur is cheap, and you bring that together, and this is an extremely high storage capacity as well. So these batteries can act as a backup supply if there is like no wind, no solar energy produced. So you need to charge that when there is excess energy, you have to charge this, and then you can release this energy stored from these types of batteries. So this will be seen, but there will be no one fits it all solution in the future. I mean, there will be countries or regions, where you have batteries. There are maybe regions where you have, water power. You pump up water to a higher altitude and then you release it later. So there will be not this single solution, I would say, but for sure, we will see improved batteries in the cars. We will have these generation 4 batteries seeing, be it lithium, metallic lithium, or solid state batteries. That will be the reality in the next 10 years. For sure, maybe even a little bit earlier. The progress now is very fast.
Yeah. And the very last question. What do you think will be the capacity of a battery, the highest level you can reach in 10, 15 years? You said solid state could be 2600 watt hour per kilo, but wait, will that be broken, that record?
That's the challenge, to be honest. I'm very pessimistic about these numbers. So 2600 is an extremely high and almost I would consider a theoretical value. I'm not really aware of a practical value. I would have to guess now, but when again lithium ion battery 120 watt hours per kilogram. Something like 500, I think, was a goal that I would remember, in some of these reports and papers. That is, in fact, a goal that we will see in the next year. So 400, 500, that's a reasonable target. Yeah.
That's pretty good.
And that would, more than triple, quadruple the storage capacity from today's perspective.
Yeah. If I had that in my car, I would come visit you on one charge, because we have a distance around 1,000 kilometers between us. So
I manage this with my diesel, so I still have a combustion engine, a diesel, so I can drive 1,000 kilometers. I need to say that's very convenient, but I'm clearly optimistic and I'm very positive, very determined that we will see this with battery vehicles as well in the future. Really, I firmly believe this. Yeah. But I mean, come on. I mean, we have just started 10, 15 years ago. Tesla was around in the late, 2008 or so when we had the first commercial vehicles there. It's not a long time if you consider that. So, and people are investing, and there is a very positive momentum in electromobility. I mean, it makes sense. It totally makes sense. And also, I had to kind of correct my vision on that, because sometime I thought, maybe fuel cells is the better option, because I connect fuel cells more the energy density, more like the combustion engine. Yeah. But I mean, it doesn't make sense when you bring it down to an overall efficiency thing, because a battery, you generate the energy and you store it, period. For a fuel cell, you need to generate the energy, you need to make the electrolysis, you need to split water into oxygen and hydrogen, you need to store the hydrogen, you need to transport the hydrogen, you need to fill the hydrogen in your car, and then you need to, kind of consume it again. And then you you lose a lot of efficiency. And I also heard a podcast about these topics of two physicists, and they were saying electromobility has a total efficiency of 70%, which is very high. Because electric motors have a very high efficiency.
Yeah.
With combustion engine, you're down with the this was it the cycle that we all learned in school. So you are
Carnot, isn't it called that?
Exactly, Carnot cycle, exactly. So you're simply bound to this. And for the fuel cells, I mean, with all these kind of storage, generating hydrogen, removing it again, storing it. So with a fuel cell, you're down to 30 to 40%. So that's really not so efficient. So the electric vehicle battery storage is the future, and it totally makes sense. Yeah.
Thank you very much. I am so happy that I'm one of the first movers in electricity on my car. It was confirmed today. Thank you.
Yeah, you're well welcome. Well,
yeah. So thank you very much for joining the podcast, Sven. I learned a lot. So I really hope the audience also learned something new today.
It was a pleasure, and it got me a lot of energy today, and I'm curious to see what other episode you will be generating in your podcast, Peter.
Yeah, and Sven, if people are interested in learning more, could they contact you, or do you have any places where you could recommend them to show up, or articles, papers they should read?
I mean, of course, people can contact me if they think I'm a trustful source, for sure.
Yeah,
I mean,
do.
I would refer to scientific paper for the real audience. There are a number of overviews, reviews, articles around in scientific literature about material science and so on and so forth. Even how you can recycle. Maybe that would be an interesting episode to talk about the next time, how you recycle these materials. That's also a big topic, because if these materials are so precious, cobalt, maybe we cannot throw them away, but we have to find a closed loop. And there is tons of literature out there, so it's not a new field in science. I can say so.
Wonderful. Thank you very much.
Thank you, and thanks for the opportunity to letting me speak today, Peter. Thank you.
Wonderful. See you.
Bye-bye.
Bye.
Thank you very much for following both this episode and the previous talking about battery materials. I have really enjoyed it and learned a lot about what goes into batteries and what are the future of solid state or new materials that can be used. If you want to learn more, you can look down in the comments below this video, where I have inserted different links to both the rock battery that I mentioned in previous zone, but also some of the things that Sven refers to. So I really hope that you'll bring your learning to a new level. Thank you for following, and hope you'll subscribe to this channel.